Good morning, everybody. I am Mrs. B. Gayathri, working as Associate Professor in the Department of H&S, Tigala Krishna Reddy Engineering College. Today, I am going to explain about laser topic, which is very important and a very interesting one. It has got so many applications in day-to-day life. Now, the main contents of this laser, which I am going to explain today, is the definition of absorption, spontaneous emission, stimulated emission, population inversion, metastable state. Second one is the characteristics of laser. Third one is derivation of Einstein coefficients. Fourth, components of laser and pumping mechanism. Fifth one is ruby laser. I mean, the types of lasers which are present, the ruby laser, helium neon laser, Nd:YAG laser, semiconductor diode laser. Finally, the applications of lasers. Okay, let us see first the acronym for laser. So, acronym for laser is light amplification by stimulated emission of radiation. The first successful operation of laser was done by scientist Lyman in the year 1960 using a ruby crystal. So he has constructed the ruby laser. So ruby laser is was the first laser constructed by scientist Lyman, which is the simplest laser. The theoretical basis of development of laser was provided or was given by scientist Albert Einstein in the year 1917. Here, we have to know about how the uh, electromagnetic radiation is interacting with matter, which is explained as the stimulated absorption, spontaneous emission, and stimulated emission. Let us see about the absorption. Here we are considering the two energy states, E1 as the ground state and E2 as the excited state or higher energy state. Now, generally we know that the more number of atoms will be present in the ground state as compared to excited state. Therefore, the population of the ground state is designated as N1, and the population of higher energy state or excited state is designated as N2, and hence the population in the ground state is more than the population of higher energy state. Now come to the case of absorption. The atoms which are present in the ground state uh, will absorb the photon which is incident on the atom with the energy h nu, which is equal to the difference between the two energy state, and they will excite it to higher energy state. Such type of process is called as stimulated absorption. If you see this figure, clear idea you will get. Now E1 is the ground state and E2 is the excited state. Now a photon of energy h nu, which is equal to the difference between the energy states E1 and E2, is incident on the atoms. These atoms will acquire that energy and they will go to, or they will be excited to higher energy state, that is E2. This is called as stimulated absorption. The stimulated absorption rate depends upon the number of atoms which are present in the ground state and as well as the energy density of photons. Okay, the frequency of photons. Now the stimulated rate is directly proportional to the number of atoms in the ground state, and it is depending on the density of photons. On the two factors, the stimulated absorption depends. The next one is the spontaneous emission. The spontaneous emission was postulated by scientist Bohr. Bohr postulated this spontaneous emission. Here also we are considering the energy states E1 and E2. E1 is the ground state and E2 is the higher energy state. Now by the absorption process, stimulated absorption process, the atoms will be in the higher energy state or the excited state. They are already reached there. The condition is that in the excited states, the atoms will not stay for a longer time. They will be there up to 10 power minus 8 seconds, which is called as lifetime. Then automatically the atoms will come back to ground state by liberation of photon, which is equal to h nu, which is equal to the difference between the two energy states, which is shown like this. Now the atom which is already present in the energy excited energy state will get will be there for a 10 power minus 8 seconds and come back to ground state by liberation of one photon, which is equal to h nu, which is equal to the difference between the two energy states. This process is called as spontaneous emission. So spontaneously the atom is coming back to ground state without any aid of external agency. Such a process is called as spontaneous emission. The spontaneous emission rate mainly depends on the number of atoms present in the excited state. Only it depends mainly on the number of atoms present in the excited state. Let us see about the stimulated emission, which is very important to understand. Stimulated emission was postulated by Einstein. So, why we concentrate more on stimulated emission is that the acronym for laser itself is the light amplification by stimulated emission of radiation. Here, not spontaneous emission of radiation. So, we here the main characteristics of laser is that here, in order to explain the characteristics of laser, these are the characteristics. So the main characteristics are that highly directional, highly monochromatic, highly intensified, and highly coherence light. In order to achieve all these things, we want the stimulated emission to happen. Therefore, we are more concentrated on this topic, that is stimulated emission, which was postulated by scientist Einstein. Here also we are considering the energy states E1 and E2. That is the ground state. This one is the higher energy state or excited state. Now, as we know that in the excited state, the atoms will not stay for a longer time. Within that lifetime, if a photon of energy h nu, which is equal to the difference between the energy state, is made to hit the atom which is already present in the excited state, that atom will come back to ground state by liberation of two photons. These two photons are having the same phase, same wavelength, the same frequency as that of the incident photon. Hence, such type of emission is called as stimulated emission. Stimulated emission. If you see this picture, here, E2 is the excited state, E1 is the ground state. The atom which is already present in the excited state is triggered by means of photon of energy, which is equal to the difference between the two energy state. Within that lifetime, the atom will come back to ground state by liberation of two photons. Whereas in the case of spontaneous emission, only one photon is liberated. In the case of stimulated emission, two photons will be liberated. These two photons are having the same phase and same wavelength, same intensity as that of the incident photon. So the stimulated emission rate depends upon the number of atoms which are present in the excited state as well as the energy density of photons. Let us see about the differences between the spontaneous and stimulated emission. So the spontaneous emission was proposed or the postulated by scientist Bohr. Stimulated emission was postulated by scientist Einstein. So here there is no additional photons are required to trigger this spontaneous emission, whereas these additional photons are mainly required to have this stimulated emission. So we trigger the atom which is present in the excited state by means of additional photon to have two photons at the output. That is what we need additional photon to have this stimulated emission. So one photon is emitted in spontaneous emission, whereas in the case of stimulated emission, two photons are liberated. Here, the emitted radiation is polymonochromatic, means it is having more wavelengths. Okay, that is polymonochromatic light is obtained. The emitted radiation in the case of stimulated emission is a highly monochromatic one. The emitted radiation is incoherent, and in the case of stimulated emission, it is highly coherent. So next is the emitted radiation is less intensified one. The emitted radiation is highly intensified one in the case of stimulated emission. The emitted radiation has less directionality, whereas here stimulated emission has more and high directionality. Example for this spontaneous emission is the light from sodium or mercury lamp, whereas in the case stimulated emission, the laser is the example. Now let us see about the population inversion, which is very, very important to achieve the laser output. So in order to have the laser output or the lasing action, we need stimulated emission. So in order to achieve stimulated emission, we want the population inversion. Okay. Let us, before going to talk about this population inversion, we all know that we are considering the energy states as lower energy state E1 and higher energy state as E2, that is excited state. Generally, the number of atoms or the population of ground state is more compared to the population of higher energy state. Let us consider N1 and N2 as the population of lower energy state and the population of higher energy state. Now, in order to achieve the stimulated emission, we want more number of atoms to be present in the higher energy state, and they get triggered and they will come back to ground state by liberation of more number of photons at the output. So in order to achieve that one, what we need is we want more number of atoms to be present in the higher state than in the ground state. But generally ground state atoms will be more compared to higher energy state. So making the population of higher energy state or excited state more than the population of ground state is called as population inversion. Population inversion. We are inverting the population, means making the population of higher energy state or excited state more than the population of ground state is called as population inversion. Now, N1, as I said, N1 and N2 be the populations of ground state and higher energy states, that are energy states we considered as E1 and E2. Now, according to general Boltzmann distribution of population, whose energy as E and at a temperature T is given by Ni is equal to N naught into e power minus Ei by kT, where N naught is the population of ground state and K is the Boltzmann constant. From the above relation, the population in the case of energy states E1 and E2 as N1 is equal to N naught into e power minus E1 by K2 and N2 is equal to N naught into e power minus E2 by KT. At ordinary condition, at general condition, at lower temperatures or at room temperatures, we consider generally it is known that the number of or the population of ground state is always greater than the population of excited state. The stage of making the population of higher energy state or excited state greater than the population of lower energy state is called as population inversion. That is, N2 is greater than N1. Now, how it is possible to make the atoms to be more present at the higher energy state than at the lower state is done by pumping or raising the atoms from ground state to higher energy state. This process is called as pumping. We make the process of rising the atoms or the particles from ground state to excited state. That is, to achieve the population inversion is called as pumping. The process of achieving the population inversion is called pumping. Pumping. In the ground state, the atoms will be more, they will be having more lifetime compared to the atoms which are present in the excited state. But to achieve the population inversion, we need intermediate energy state. Between lower energy state and excited state, there is an intermediate energy state which is called as metastable state, where the atoms has where the atom has more lifetime. Hence, it is called as metastable state. So, metastable state is essential in the case of lasing action. To achieve the lasing action, we want population inversion, we want stimulated emission. Stimulated emission can be achieved by means of population inversion. The population inversion can be achieved by means of metastable state. So, let us see there are three level and four level energy states which are present. Let us see about this. Here the population's inversion at normal condition, N1 and N2 are the number of atoms or the population present in energy states E1 and E2. N1 is greater than N2. From this diagram, it is clear. Now, after population inversion, what happens? The population of higher energy state will be more than the population of lower energy state. Here, this is the metastable state. If you consider at normal condition, N1 is greater than N2. But population inversion, once it has happened, then N2 is greater than N2. The population of uh, intermediate energy state, that is the metastable state, will be greater than the population of lower energy state. This is when suitable energy is supplied to the system, atoms will get excited to the energy state E3, and after their lifetime, they will come back to energy state E2. Therefore, the E2 energy state will have longer lifetime compared to E3, and hence it is called as metastable state. So, these are the main thing which is happening to have this lasing action. Let us see about the characteristics of a laser. In this case, in the case of laser, uh, mainly how it is to be discriminated from normal light is it has got special characteristics like highly directional, highly monochromatic, highly intense, and highly coherent. Let us see. Highly directionality. The light ray, if we consider a torch light, okay, when torch light is on, what happens? The light is spread out in all the direction. For 1 kilometer, when the light of this torch light is travels 1 kilometer distance, it spread around 1 kilometer wide. The widening of light takes place with a torchlight or normal light. But when the laser light spreads a few centimeters distance, even it has traveled lakhs of kilometer distances. Therefore, it is highly directional. It is highly directional. So the widening of light will not be more. The angle of what we can say, the angle will be less. Divergent angle will be less. It is less divergent. The light is less divergent. If we consider this figure, the directionality of laser can be expressed in terms of divergence phi, which is given by arc by radius, that is d2 by d2 minus d1 by S2 minus S1. Next is highly monochromatic. As I said, monochromatic. Mono means single, chromatic means color. So monochromatic, single color means single wavelength. In laser radiation, all the photons emitted between discrete energy levels will have the same wavelength. That is the main special characteristics of this laser. As a result, the radiation is monochromatic in nature. Due to this stimulated characteristics of laser light, the laser light is more monochromatic than that of conventional light, that is normal tube light. Okay, so the laser light wavelength spread is around 0.001 nanometer. Therefore, it is so clear and it is having highly monochromatic. Let us see about the next characteristics, which is highly intense. So, if we consider laser light, which is highly intensified as compared to normal light. So, in the case of, for example, if you consider 1 milliwatt helium neon laser, which is highly intensified than the sun intensity, when two photons of each amplitude are in phase with other. The resultant amplitude is two photons, and its amplitude is doubled in laser. So, in that way, we can say that the laser is highly intensified. The laser light is highly intensified as compared to the normal light. Next is the highly coherence. The coherence is the property of wave which is being in phase with itself and another wave over a period of time and space and or distance. There are two types of coherences. One is the temporal coherence, the other one is the spatial coherence. So the so in the case of temporal coherence, which is also called as uh, longitudinal coherence, here we are considering a single wave which is maintaining the fixed phase relation uh, between the laser source at different times at two different points on the same wave. That is called as the temporal coherence. If you see P1 and P2 are the 2 points which are on the same wave, they are having the same phase relation and maintaining the same different. They are at the different times. Then it is called as temporal coherence. Next one is the spatial coherence. Spatial coherence is also called as transverse coherence. The photons emitted from laser source maintaining a fixed phase relation at different locations. Means we are considering the 2 points on different waves. That type of coherence is called as spatial coherence. Temporal coherence means we are considering a single wave having at a different positions, maintaining the phase with the time. Okay, here different locations can be considered, different two waves can be considered, and they maintain the fixed phase differences or phase relations. Such type of coherence is called as spatial coherence. Coherence is nothing but it is the phenomena having the what we can say, if you consider the two sources, if the two sources are maintaining the same phase difference or they maintain a constant zero phase difference between them, then these two waves will superimpose on each other by using Young's experiment. When they superimpose on each other, what happens? They reinforce with maximum intensity. Therefore, we are having highly intensified light at the output. Next is we are going to see about the pumping mechanism, or we say this the there are different types of pumping. Pumping means we are raising the atoms from lower energy state to higher energy state in order to achieve the stimulated emission and in order to achieve the population inversion that is done by raising the atoms from ground state to higher energy state. That process we call it as pumping. So there are different types of techniques to have the population inversion by means of pumping mechanisms. So Here we are going to see about different mechanisms. Uh, Here, first one is the optical pumping, second one is the electrical discharge pumping, third one is chemical pumping, fourth one is injection current pumping. So we will see one by one. Optical pumping. So optical pumping is used in solid state laser. So the solid state laser example is the ruby laser is the one where we use this uh, optical pumping. So on the ruby rod, xenon flash tubes are used for optical pumping. So these materials have very broad band absorption, sufficient amount of energy is absorbed from the emission band of flash lamp. So the examples, as I said, ruby laser, NdAg laser, ND glass laser. That is the optical pumping. So it is mainly used in solid state laser. Next is the electrical discharge pumping. Electrical discharge pumping is used in gas lasers. So the since gas lasers have narrow absorption band pumping, they them and any flash lamp is not possible. So electrical discharge is pumped, which examples are helium ion laser, CO2 laser, argon ion laser. Means we make the electron to be electron to excite the atoms which are present in the ground state to higher energy state. That such type of pumping is called as electrical discharge pumping. Next is the chemical pumping. Chemical reactions may also result in excitation and hence creation of population inversion in few systems may take place. Examples systems are HF and DF lasers. And next one is the injection current pumping. So mainly we use such type of pumping in the case of semiconductor lasers. So injection of current, we are supplying current at the junction, through the junction. Therefore, more number of electron and hole pairs can be generated, and hence population inversion among the minority charge carriers occur. Therefore, we are going to have the laser output. The example of such systems are indium phosphide and gallium arsenide. These are the types of the pumping mechanisms which are present to achieve the population inversion in the case of laser. In the case of laser. So in the next class, I'm going to explain about the different Einstein. As I said, Einstein was the person who has given the theoretical idea about the stimulated emission. So we are going to see about how he correlated the mechanisms, or the what we can say, how the radiation is interacting with matter into an equations called as Einstein coefficients. I think all of you might have understood the concept like stimulated absorption, stimulated spontaneous emission, stimulated emission, the differences between spontaneous emission and stimulated emission. We have come across the population inversion, metastable state, and the pumping process, and different techniques used for this population for pumping the atoms to achieve the population inversion. Those are all explained in this lecture. I hope that you understood it clearly. Thank you, one and all.